of the audience have seen this, perhaps a few weeks ago, or seen one of the many collaborators give a talk on this. But hopefully I can shed some light on this project that started, as I was just telling Christopher, at the American Institute of Mathematics at a workshop on moduli. Actually, Dan left. Dan Halpern-Leifner was just here. He was one of the organizers of this workshop. And so that's why it's sort of the big group of people. The paper we put out earlier this year, and tell you a little bit about the project that we did, what we are trying to do now, and if there's time at the end, maybe some applications to other projects. So everything that I will say will be joint with these 6 people: Kenny Asher, Dori Baleri, Harold Bloom, Giovanni Inchiostro, Yuchen Liu, and Xiaowei Wang. And if I forget to mention all 7 of us, it's a big group. But what is this project? So I'm going to tell you about moduli of Calabi Yaus, and particularly some objects we called boundary polarized Calabi Yaus. And to start out with that, though, I think it would be a better place to start. This is maybe more colloquium style with what we know about moduli of different types of varieties. So also, everything that I'm going to say, we're working over the complex numbers, and I won't have to worry about any other field. But what we know about moduli of varieties is we usually start with the kind of standard trichotomy, where we break varieties into 3 types. And I'll make more precise definitions as we go on, but this is maybe just motivation. We have canonically polarized. So there's some variety X where the canonical divisor is ample. Maybe X is smooth, maybe it's singular. Again, I'll make precise definitions in a minute. You can also do this for pairs XD, where KX plus D is ample. So these are our analogs of higher genus curves or high dimensional surfaces in projective space, or many, many other things. Our next piece, I'm going in some order relevant for the rest of the talk, I think, but we also have Fano varieties. So the opposite notion, minus KX is ample, or log Fano pairs, XD, where the log canonical divisor is anti-ample. And then the third case that we'll be talking about today are, I will sort of call these Calabi Yaus, maybe K-trivial is a better word. So X, where KX is, for now, we'll just say numerically trivial, or similarly pairs, XD, where KX plus D is trivial. And once we've broken things down into these 3 types, we would like to make moduli spaces of each of these objects. So fixing some numerical invariants, looking at all of the canonically polarized varieties with those numerical invariants, and constructing this parameter space of all of those objects. And we can essentially do this in cases A and B. So we can do maybe moduli spaces, but also I guess we'll be talking about stacks today. So we may have a moduli stack or a moduli space, and these go under different names and different tools in the different cases. So in the first case, canonically polarized varieties or canonically polarized pairs, we have the KSBA or KSB moduli stack / space. So I'm going to be sort of loose about this at the moment. Again, I will give you precise definitions, but we have this curly M KSBA with an N and a V mapping to a Roman M KSBA and V. And what are these? This is a moduli. This happens to be a DeVleming-Mumford moduli stack. This parameterizes, I guess, I haven't told you if we're talking about pairs or spaces. So let's just say we're talking about varieties right now. X with dimension n, volume kx to the n equaling v, and the stability condition to be in this stack is that x has SLC singularities and kx is ample. I sort of wrote these in maybe out of order, but it parameterizes these objects. It parameterizes all of the moduli, all of these canonically polarized varieties of this fixed dimension and volume, and it has this map to the projective coarse moduli space. So the coarse, I mean, this is it's like theorem of Kiel and Mori that we have, for this canonically polarized case, we have a coarse moduli space, which if you don't know what that means, we have a bijection on the C point. So somehow, this is a stack, it does have some extra structure. This is a projective variety, so I said it's projective coarse moduli space, but it is actually the variety here, and they somehow contain roughly the same information. There's nothing lost in this morphism. So they parameterize the same collections of objects here. And the KSB is Kolar and Shepard-Barron, and the A is Alexeyev. So Kolar, Shepard-Barron did this for really surfaces. The A, if you look at Kolar's moduli book now, there's several different notions of stability. The KSBA is the case of pairs, which will be the case that we're talking about, among other things. And we have these moduli stacks. They are relatively well understood, and I say that with the major caveat that we have essentially no examples of complete descriptions of what's in these moduli space. So they're well understood as a theoretical object, but maybe for people interested in explicit moduli, like even just for surfaces, having a complete description of everything that's parameterized by the boundary is very difficult, if not intractable. So that's one side of the picture. And as we go to the different cases, so as we move from the general typesetting to maybe the phono setting, we can still do this, but the moduli picture gets a little bit more complicated. So case B, we have in the phono variety, we have k moduli stacks and spaces parameterizing phono varieties. So I should be careful what I write here. Jin-Young saw me give this talk a couple weeks ago, but this is the theory, maybe with Chen-Young at the center and many other contributions to the theory of k moduli. But what is k moduli? It says I have two different stacks. Now I have, I'll put a KSS, I'll define this in a second, and V mapping to a space, Roman M, KPS, and V, where this is an Artin stack. It's no longer Deligne-Mumford, parameterizing K semi-stable phono varieties, maybe X with dimension N and anti-canonical volume V. I'll say something about K semi-stability in 1 second, so hold on to there. And then we have, again, a projective moduli space that called a good moduli space. A good moduli space is worse than a coarse moduli space. So I'll say a little bit about what that means momentarily, but we have a projective good moduli space that parameterizes the K polystable objects. Okay, so most of the K moduli theorem, namely the existence of this moduli space and this moduli stack, is very recent. The projectivity was what, 2022, or sorry, the properness was 2022, 2021. Most of this theorem is very recent. And what is K stability, though? Unlike many of us birational geometers, maybe are comfortable with just SLC singularities. I throw out that word like we know what it means. K stability is a little bit more subtle. It turns out that K polystability this is a theorem that comes from differential geometry, and only if X admits a Kähler-Einstein metric. Maybe X could be singular, so there's some notion of a singular Kähler-Einstein metric But it's something that is non-trivial. Not every Fano variety admits one of these metrics. Okay, so it has several implications. And I, again, will do the thing that everyone in case stability talks does. I won't define case stability, but I will tell you some implications. So, for example, if it's a theorem of Odaka, that says if X is K semi-stable, or there's a notion of all of this for pairs, and the K moduli theorem also works in the case of pairs. So either these K semi-stable mean that they have KLT singularities. So in particular, the spaces that are parameterized here are all normal. You don't have SLC where you have many components glued together. All of the objects parameterized here are normal. Also a theorem due to many people, Alper, Bloom, Halpern-Leisner, and Shu, that if X is K polystable, then the automorphism group of X is reductive. So those are, I mean, I don't know if this will help you understand K stability, but at least these two conditions tell us that not every Fano variety can be K semi-stable. If you take P2 and you blow it up at one point, the automorphism group is not reductive. So it turns out to not fit into this criteria. So the K moduli stack itself parameterizes Fano varieties with these sort of very nice conditions. And it turns out that K semi-stability is sort of exactly the right algebraic notion to get a well-behaved moduli stack. It gives you reductivity of automorphism groups, which helps you write things as quotient presentations. It gives you boundedness. It gives, via the KLT, it gives you many conditions that you want in order to have an Artin stack, and then this associated good moduli space. But as I said, I would come back to the word coarse is here. The word good is there. Good is worse. This is not a bijection on points. Similar to, if K stability looks sort of similar to geometric invariant theory, you have many semi-stable points that get mapped to the same polystable representative. So you look at things that are sort of having the same closed orbit. I say sort of exactly things that have the same closed orbit, and you map them to the unique representative in that closed orbit. And this is sort of the notion of what a good moduli space is. This is introduced by Jared Alper, and it roughly says that that's what this map does. It identifies certain points with different orbits under the automorphisms and maps them to points with closed orbit. So that's what we know. I mean, all the details, even in this case, were sort of only recently settled, particularly over how to define families over non-reduced spaces. And this is very, very recent, like within the past year or two, that all the details here are settled. So even in that case, right, math moves on. And the question is, can we do this for Calabi Yaus? Is there a natural notion of a moduli stack and a moduli space and a stability condition? So here the stability condition is SLC with ample canonical. Here the stability condition is whatever K semi-stability is. Is there a notion of a moduli stack and a moduli space that will capture the picture for the Calabi Yau case or the K-trivial case? And that's where the project started. But to maybe motivate what our definitions will be, as some of you maybe already know, in certain settings, the Calabi Yau case sits in between the Fano case and the general type case. We'll make this precise momentarily, but we may hope to sort of leverage this construction and this construction, if we can make a Calabi Yau sit in between, to make a Calabi Yau moduli space. And that is building off of, so I guess this was really the starting point of the project, work of myself and Kenny and Yu-Chen in the case of hypersurfaces in Pn, but in particular the case of curves in P2. We'll start with that. So maybe this is still sort of a motivational conjecture, which does, this conjecture does follow from the work that I'm presenting, but motivational conjecture that was in my paper with Kenny and Yu-Chen, that The Calabi Yau space sits in between the KSBA and the K-moduli space in a precise way. So I need to introduce some notation before I can say that. We're looking at stacks. I will say, we'll introduce 3 stacks. So we have a curly P. I'll put H, D. All right. So I'm going to do something a little bit sloppy. Hopefully this will make sense, but please ask questions. I'm going to write a stack in terms of a set of the objects it parameterizes instead of talking about families. So this will be pairs X 3 over D plus epsilon D, such that X is a Q-Gorenstein degeneration of P2. D is numerically, well, we'll write it like this. Kx plus, okay, let's put my D on the right place. D Kx plus 3 times D is linearly equivalent to 0. So D is an integer. D will be a degree. And we'll say that X, I guess we should say X is a mono Q-Gorenstein degeneration of P2. And D is, I guess, this condition plus this condition, so that D is ample. Oh, and I didn't put the stability condition. The stability condition is that this pair is SLC with this coefficient epsilon. So PDH, this is a stack of these objects. The H stands for either Hassett, who did this in degree 4, or Hacking, who did this in all degree, which proves that several things. One, this is independent of epsilon for all epsilon sufficiently small. So I didn't define epsilon for a reason. I didn't need to. And it parameterizes all of the pairs that essentially arise as degenerations. So I guess one could sort of think of this as KSB A degenerations of the pair P2 and some degree D plane curve. So this is a KSBA moduli stack of these objects. And this, one way to think about this is, I mean, 3 over D plus epsilon, this is just barely log general type. We just added a little bit of epsilon to make this canonical divisor Kx plus 3 over D plus epsilon ample. And what Hacking studied and what he was able to show is this is sort of a minimal moduli space, and he, in low degree, was actually able to describe everything that appears in this moduli space. So this is one side, and then conversely, and so I guess also by the general KSBA theory, this has this moduli space. So this is, I'll use Roman M's for the moduli spaces and kind of curly letters for the moduli stacks. But conversely, you can do the same thing with a minus epsilon with the theory of K stability. So the paper that is being referenced with Kenny and Yuchen does this. We set up a wall crossing framework for K moduli, and we get a PDK, which is pairs X 3 over D minus epsilon D, where again X is Fano Q-Gorenstein degeneration of P2. D times Kx plus 3D is trivial. This is just capturing that D is really a degeneration of a plane curve. And then again, D is ample, but the stability condition here is that this pair is K semi-stable. And so not every plane curve you're going to write down is K semi-stable, but in any case, you have the K moduli space, and then this has a map to, the K moduli stack has a map to this K moduli space, which parameterizes the polystable. Okay. So what one may just naturally guess is that these are two sides of the same picture. We have 3 over D plus epsilon, 3 over D minus epsilon. I can just let epsilon go to 0, and then I should get a, quote, Calabi Yau moduli space. And in some settings, this is like quite literally a moduli space of Calabi Yaus, which I will mention momentarily, even though this is a very specific example. So what we conjectured in the paper, and we were able to prove in, I guess, degree 4 and 5, and maybe Alexeyev told us that he could prove it in degree 6, which we didn't write down at the time, but what we conjectured is that there exists, so maybe I'll call this the conjecture. A diagram that looks like this. So we have P, the hacking plane curves of degree D. This sits inside a bigger moduli space, which we'll call PCY of degree D. We have the K moduli space, these pairs of curves of degree D, and these all map to their appropriate moduli. I said space, I meant stack for that whole row. These all map to some appropriate moduli space, and the conjecture is there exists one, just the center of this diagram. There exists something I can put here that's some sort of well-behaved stack, and there exists something I can put here, but the conjecture is actually finer than that, this thing at the bottom, this PDCY, I'll just continue to write this in green. This is the ample model. So these are both projective varieties. There's a natural line bundle on these varieties called the Hodge bundle. It's a Q line bundle, I guess, but this is just the ample model of the Hodge bundle on either side. And furthermore, we do, by virtue of the description of the K module, so I guess I'll pull this up for 1 second, and then I'll scroll back down. So we have some conjecture on what that bottom space is. It's this, you can take the Hodge bundle on either side and just take proj of its canonical ring to construct this variety. But also the thing on the top, there's a natural guess for what it should be. It's supposed to contain this hacking moduli space and this K moduli space. The space on this side parameterizes at least pairs with SLC singularities. I guess these specific pairs. Deal modulo some Q factorial issues, which we don't have to deal with in this case. As epsilon goes to 0, that still remains semilog canonical. On this side, the K moduli space, by Odaka's theorem, the pairs that are parameterized for small epsilon are KLT. So as epsilon goes to 0, they remain log canonical. So not only do we think that the ample model of the Hodge line bundle gives you this projective variety, but then also this upper space just parameterizes, sort of necessarily has to parameterize pairs x3 over d, where this is SLC in this particular coefficient, and still x is still one of these Q-Gorenstein degenerations of P2, and it still satisfies the condition that d times kx plus 3d is 0. But I mean, even in this case, this is a bigger stack than just the union of the two things on either side. There are things that satisfy those conditions that you cannot modify, perturb by epsilon, and land in either of things on either side. So anyway, in this paper, where we study K moduli of pairs for a Fano ambient space and an ample divisor, we made this conjecture and proved it in degree 4, degree 5, and then half of degree 6. And then Alex Ab told us he had a proof of the other half. So we expect this to hold for many reasons. One, we have low degree evidence, and two, more geometrically, we have a complete description of how the two things on the left and the right side differ. We know exactly what's here that's not here, vice versa. And so we believed this. But again, this is special to the place of plane curves. We expect you can do something like this in more generality if you have pairs x comma d, where d is ample and kx plus d is trivial. So that's sort of where we are, and the starting point of this work. And so ultimately it led us to the objects that we are going to study for the rest of the talk, which maybe I should just define. I have in my notes just so I can give examples. I'll define it first, and then I'll give examples. So the objects that we're going to study in this talk are some analog of this PDCY. So we'll call this a boundary polarized log Calabi Yau, which we will immediately start abbreviating as BPCY, is a pair x delta plus d. I guess certain people in the audience we're defining essentially an SLC log Fano with a complement. So that's it. This is all it's going to be. But for whatever reason, in this paper, we called it boundary polarized Calabi Yau to indicate something else about the geometry. So it's a pair with this where delta and D are effective. And the pair is SLC. I did this in some sort of arbitrary order, but that's okay. D is ample. So this is the boundary polarization that we're talking about. And Kx plus delta plus D, here we relax any sort of assumption on being linearly equivalent to 0. We'll say Q linearly equivalent to 0. So the one thing to point out here, I guess, is that this says that these two conditions say that Kx plus delta is ample and that X delta is SLC. So we could say that X delta is an SLC log phono. So we have some sort of phonotype. I don't mean phonotype, that has a definition. We have some sort of phono-ambient space, maybe a log phono-ambient space, and we're adding a boundary divisor to that we're going to use our polarization. In the case of these plane curves, delta is 0. There's no delta. X is just P2, or the degeneration of P2, and D is the plane curve, or the degeneration of the curve. Unfortunately, like, you have to have a delta, much like most people who do moduli. No, you encounter something non-normal, you have to normalize, that becomes a delta. There has to be a delta. There's no getting around it. But these are the objects that we make moduli spaces of. And what I would like to point out before I tell you the construction of the moduli space, just in the setting that delta equals 0, right, we're looking at pairs XD, where X is some SLC variety where minus Kx is ample. For me, phono just means minus Kx is ample right now. And D is a boundary that is itself ample. But D is, I guess, in this linear system. I'm not being careful about the coefficients at the moment, but if delta equals 0 is this. And this seems like maybe a strong assumption, but in fact, essentially all of the Calabi Yaus we care about, all of the SLC Calabi Yaus will arise in this way. Yeah? So they are, yes. So like the canonical example maybe in this case would be the limit of a family of curves, like let's say like D is 4 or something. You could take a limit of a family of, let's see if I can get my numbers right. Yeah, so if you look at just a pair P2 and then a curve 3/4, like I guess an A3 singularity, the log canonical threshold of this curve is exactly 3/4. So you can't add epsilon to it because it will no longer be on this side. And this example, it turns out when you subtract epsilon is still semi-stable, but you can do, if you want something strictly that appears in the middle and not on either side, you can take the union of two cones as your ambient space. So this is just two quadrant cones glued together along a ruling, and take a curve with the singularity on each component. So you can, I don't know, C1 union C2, where each has an A3 singularity. Oh, put up my coefficient here. So the log canonical threshold of that singularity is 3/4, so you can't add epsilon, and the surface is not normal, so you can't subtract epsilon. But this brings up actually quite a good point for where we'll go later in the talk. Essentially, this is the only problem. This is exactly how these differ, where you have non-normal surfaces and curves whose log canonical threshold is exactly that boundary, or in higher dimensions, the same analog. Yeah. Other questions? So the less you think we're just talking about plane curves, we will restrict to just plane curves sort of momentarily, but at least the setup and actually the construction of the stack works in much more generality and captures, I guess many like true Calabi Yau objects. even though we're saying that we're putting them in this pair, right? In the sense that, we sort of have low degree examples. If the degree is 3, and you're just talking about plane curves, right? These are our elliptic curves. So this is some kind of Calabi Yau, and yes, the curve itself is not one of our boundary polarized Calabi Yau pairs, but P2 and this curve, I guess I should put C3, is our boundary polarized Calabi Yau. Right? And similarly, if you have a quartic surface in P3, so a generic quartic K3, we could consider in this framework with P3 and the surface. And in fact, actually so this is one of the other papers with Kenny and Yu-Chen, any quartic K3 surface admits there is a natural Fano ambient space that is a degeneration of P3 that it lives in. So there is something else you can put there, but lest again you think this is sort of too specific, take your favorite K-trivial Calabi Yau variety, you can embed it as an ample boundary in the cone over that variety. So again, we'll say D is some sort of SLC Calabi Yau with some polarization. Maybe we'll call L. Then you can construct X, which this is the notation from one of Kolar's books, CPXL. This is the projective cone. Oh, sorry, CPDL over D with respect to L. And it turns out that the pair XD, where D is the hyperplane section at infinity, is an SLC BPCY. So even though we are, doing the setup where we have this Fano ambient space, you can do this, and what we are currently work in progress is going to construct moduli spaces of polarized Calabi Yaus in this way and see what happens. But what can I tell you? What did we do in this project? Well, we did two things. One thing, we constructed a stack that parameterizes all of these objects. So in some sense, we constructed the general version of this. And in some cases, we can do this. In some cases, we can prove this does not exist. So let me tell you a little bit about that. Oh, it's only 2:33. So okay. So let's see if I want to write all of the indices carefully. Using these boundary polarized Calabi Yaus, there is one number that I didn't tell you. I guess also, much like the theory of complements, sometimes you're not just interested in when this is cumulatively equivalent to 0. You're interested in when it's actually equivalent to 0. So if there exists an n, a positive integer with n times kx plus delta plus d actually linearly equivalent to 0, we say, at least this is the terminology we use in the paper, but we say this BPCY has index dividing n. So what we can do with this number n is, okay, I'm calling this a definition. Yeah, there exists a moduli stack, which depends on several parameters. So we'll say M, it depends on a Hilbert polynomial, a capital N, and two rational numbers, R, S, and Q. And I will tell you what all of these things are. There exists a moduli stack. Okay, this is what I did in my notes. So excellent. Of pairs X delta plus D, where I know they're not, yeah, anyway, where x delta plus d is one of our boundary polarized Calabi Yaus, and the Hilbert polynomial is this Hilbert polynomial chi. So instead of fixing the volume and dimension, it turns out to actually just be easier to just fix every term in the Hilbert polynomial. This pair has index dividing n, capital N, and the R and the S are in Kolar's book. He calls this a marking. So R is like the coefficients of the divisors in delta, and S is the coefficient of the divisors in D. No, so they can be. Yeah, so R and S are, it's like a vector valued function. Yeah, yeah. But the case that we'll be interested in, mostly applying this, is, I mean, it works if you fix R and S to be like the denominator of all of the things that you write down. So you could fix just a number. But yeah, so so I guess I'm saying that, yeah, I didn't want to list the theorem yet, but okay. The theorem is that one, this will be a stack with good properties. For now, there's a set of these objects, and it turns out you can actually define a stack of these objects. You have to be careful, much like in the theory of KSBA. How do you define families of these objects? And you require some Kolar conditions, some K-flatness, some et cetera, et cetera. But there'll be a theorem momentarily about what this stack, what we know is about this. But just to ground us, the case of interest will be where we're talking about like I guess pairs that are limits of P2 and some divisor 3 over D and C times D. So in this case, N will be D, and R will be 0. There's no delta, and S will be 3 over D. So this is the case that we'll sort of be the most interested in, and chi is the Hilbert polynomial of this. You can write down. But yes, as Joaquin was just asking, there's really a theorem here, namely that the stack actually has good properties. This has the right to be called a moduli stack. So I guess the first thing that we prove about this, so this is with all the all 7 of us, that this is a locally finite, this M, which I'll just call M at the moment, M chi n RS is a locally finite type Artin stack with affine diagonal. So this is some sort of technically stack condition. And then some more technical conditions. So I'll just write them. I'll say something about them momentarily. So furthermore, M is S complete, theta reductive, and satisfies the existence part of the valuative criteria of properness. So I think this is called universally closed. So I want to tell you a little bit about what these conditions are and why it is important that we verify all of them. So this is a moduli stack. It is a stack of all of these objects. Again, I didn't tell you what families of objects are, but there's a way to define families of these objects to get a well-behaved stack. And you get an Artin stack that's locally a finite type. So a neighborhood of every point is sort of finite type. And it has affine diagonal. This is a technical thing which we will apply momentarily, but it satisfies these extra conditions. So in one sense, it's quote proper. It's not finite type, so be careful what you say here. But it is a proper stack, or morally it's proper, and it is S complete and theta reductive, which are, if you have never seen these before, what S complete and theta reductive are, these are evaluative criteria over punctured surfaces. So much like properness or separatedness you detect with punctured curves, there are 2 particular surfaces, S and theta, that if you remove one point, you can ask, can you map the surface into your space and extend it over that point? So why do we care about these technical conditions without defining them? I will tell you why we care about them. Part of the goal in this construction is not just to construct the moduli space, or sorry, moduli stack, but it is to construct the moduli space. And it turns out that these two conditions are almost equivalent to the existence of a good moduli space. And so without defining them, that's one way you could actually interpret them. So this is a theorem due to Alper, Halpern, Leisner, and Heinloth, that if, it doesn't quite apply in this case, but if M is a finite type Artin stack with affine diagonal, then M admits a separated good moduli space if and only if M is S complete and theta reductive. So these two technical conditions, which are these two valuative criteria over surfaces, at least in the finite type case, tell you precisely when you have a good moduli space. Meaning what is a good moduli space? Well, I mean, I never really defined this, but a good moduli space is essentially what we want in many cases. It's a map. The definition is not particularly illuminating. This map is cohomologically affine and is exact, like the push forward of O is O. So the definition doesn't really tell you anything. But what a good moduli space is that geometrically it identifies two elements in the moduli stack if and only if their closures intersect in that stack. So even though that's not the definition of good moduli space, that is the consequence. Two elements in curly M get identified with the same point in Roman M if and only if their closures intersect. So in terms of moduli, even if you think about like geometric invariant theory, that's the exact notion we're trying to capture. So if you look at what we prove about our moduli stack of all of our objects, and that theorem, we have almost all pieces. We have an Artin stack with affine diagonal, as complete and theta reductive. But the big problem with our result compared to their result is that M is almost never finite type. So their result does not apply. And in fact, we actually have examples where, in the sense of Alper, it will not admit a good moduli space. So I can say something about that, but let me tell you a little bit about the counterexamples to finite typeness and how we get around it, at least in the plane curve case. So in our setting, we want to know, I mean, this M is just typically not a finite type, even in sort of the first example you write down. So we want to know, does there exist something that acts like, I'll put it in quotes, because it turns out it won't actually be literally a good moduli space, but it'll be something close. So why do I know this is not finite type? The simplest example is we will look at the case of elliptic curves. We're going to look at curves in P2. So if I look at curves in P2, degree 3 curve, the boundary polarized Calabi Yaus that we're getting they include many different things that you might not expect, but the first thing that happens is you can imagine, right, our boundary polarized Calabi Yaus are allowed to be SLC, so the curve can be nodal, the curve can be mildly singular. So one specific curve I could take is just P2 and 3 lines. Right? So I guess I could just write this as like X, Y, Z. equals 0. This admits infinitely many degenerations to other boundary polarized Calabi Yaus. Namely, you can sort of do two things, and then you can start combining the things and get more. One thing you could do is degenerate the curve to have more pieces. And if you're careful and use some toric geometry, you can also, there's a surface that goes along with this, right? So your curve can go from a triangle, you know, to a square, to a pentagon, to continue on as far as you want. That's all fine. So you can imagine sort of degenerating the curve. You do have to be careful about what happens with the surface, but anyway, that's the one thing you can do. You can also degenerate the surface itself. So you can degenerate P2 to the surface P a squared b squared c squared with also 3 lines, x, y, z equals 0, where a squared plus b squared plus c squared satisfies the equation 3abc. And there's infinitely many of these. So we have unboundedness in sort of many ways. And just to give you a very concrete picture, which I will leave up on this board, you can imagine starting with just P2 and these 3 lines. You can degenerate this. You can actually degenerate P2 to a union of 3 broken surfaces, weighted projective planes, and I should use some color here. Again, the sort of boundary at infinity here. Those look like those intersect. Let's try one more time. Okay. You can also degenerate the surface to this infinite union. So we'll just write the first one, P114, which is a cone over a rational normal curve, and its toric boundary, x, y, z equals 0, which is, in this case, the section at infinity and 2 of the rulings of the cone. And both of these kind of behavior you can extend. So even in the simplest case, our stack is not finite type. And we may want to know, how do you build a good moduli space when it's not finite type? In degree 3, we know what the answer should be. This is a moduli space of elliptic curves. We know what the answer is. And pardon? Yes, exactly. But it's not quite, it works from the theory of stacks, but it's even, this is not even like a coarse space on the general fiber. So because of the way we define this, okay, we know if this is M, this is what M is parameterizing. This is Roman M. This is our point at infinity, right? This is P1. I mean, this is our P1. This is what it has to be, right? If we actually defined a correct notion, the moduli space of genus 1 curves, it's going to have to be P1. But we have, in the stack, we have an unbounded number of things above the point at infinity, but even at a general point of, general J invariant, maybe I'll just put J or something. The plane curve pair, we maybe take P2 with this degree 3 curve. This is not the closed point. This degenerates, if you think about, is it still there? This construction, this further degenerates. We're not requiring the generic fiber of the family be KLT or anything like that, right? Any SLC is allowed. So this degenerates to the cone over this, genus 1 curve with its boundary. So this is the cone over C3. So, even though, and granted, this doesn't provide any problems, really. There's not an unbounded number of things over the generic point, but over the generic point, the plane curve, the closed point is the cone over the elliptic curve. It's not the plane. So how do we construct a moduli space? How do we do it? And we do essentially what was just suggested, and actually what's sort of a miracle is this works always. It turns out for any degree plane curve, for any degree that's a multiple of 3, where you have this unbounded behavior, you just have to put in 1 point. So what we are able to prove, I guess we'll just start here, is that at least in the case of plane curves, and in some amount of more generality, there does exist a good moduli space. Oh, we're running out of time, so let's give you some of the punchlines here. I guess maybe this seems more miraculous than anything, but the main theorem, at least in the plane curve case, we can do, if I call this PDCY, let's say this is our moduli space, just this one component of this, M chi d 0 3 over d main component of, now we're parameterizing these degree d plane curves. Oh, moduli stacked. I haven't gotten to the space yet. Admits what we call an asymptotically good moduli space, which we can call Roman PDCY. And furthermore, on this PDCY, the Hodge line bundle is ample. So this is projective. And our motivating conjecture and motivating conjecture about this existence being the ample model of the Hodge line bundle holds. Okay. So I have about 10 minutes left, and what I'd like to tell you is what's an asymptotically good moduli space and how we construct this. And if there's time at the end, I'll tell you a little bit about either some applications or what we expect beyond the case of plane curves. Are there any questions on the statement? Yeah, not yet, no. But it turns out in order to prove this theorem, which I'll write down in just a second, is that what we prove is that if you imagine this in terms of type, like type 1, type 2, type 3, in terms of the dimension of the source or the minimal log canonical center, we prove that all of these maximal types with this minimal dimension of the source are equivalent to just that guy. So this is not a closed point in any way, but you can think of it as the representative point there. So that's really the key. So the key to proving this theorem is two pieces. Namely, one, we can prove that this, I guess these words I just threw out to James, the regularity or the dimension of the source, or the type, as long as that is controlled, there just exists a good moduli space. Everything is finite type. So I guess we could say the definition, let's say x d. You can put a delta here, but let's say it's one of our boundary polarized Calabi Yau. I mean, this exists in more generality, right? But the regularity of x d is the dimension of x minus the dimension of the source minus 1, if I got all the minuses correct. And so the source, this is the, I guess, the minimal log canonical center in some DLT modification. Pardon? Did I get it backwards? Is this co-regularity? Okay. Okay. Co-regularity, co or regularity, whichever one. So thanks, Joaquin. And so what we prove is that actually, I guess we prove that for any of our, not just the plane curve case, but if we look at m less than or equal to 0, which is the set of pairs, I guess this is contained in this, our big Roman M with all of its markings, where this is just where this co-regularity is less than or equal to 0. Then this is finite type. And even though it's a substack, it is still S complete and theta reductive. So we prove this, and then as just we can just directly apply the result of Alper, Haupenleister, and Heinloth, which just says that the M less than or equal to 0 admits a good moduli space. We don't have to deal with any of this complicated thing at the boundary. So what that's saying is, at least in this picture, everything away from the central fiber at infinity is part of M less than or equal to 0. So if I just cut out the central fiber, there exists a good moduli space, which there just does. You just identify the closed point in each orbit, and then you parameterize. Okay? So the only thing we have to do is deal with that point at infinity. But in fact, you only have to deal with this in special cases. So we only have to say that, I guess maybe this is a proposition, I don't know, proposition. If we're looking at this PD, PCYD, okay, let's try to make this an actual sentence. If D is not a multiple of 3, then our stack of at least the plane curve case is just equal to the stack of co-regularity less than or equal to 0. So provided that D does not divide, 3 does not divide D, this PDCY admits a good moduli space. And so the only thing that we have to do is deal with everything else. And at least in terms of surfaces, this co-regularity can be -1, 0, or 1. So this deals with 2 of the 3 cases. And then how do we deal with the final case? We prove that the regularity 1 objects, or excuse me, the co-regularity, are all S equivalent. So all are common degenerations of just that pair at the very top center. So then what we prove, I mean, we actually do a lot more. We describe in the paper essentially all of the S equivalence classes. So for any degree, not just degree 3, but we prove that if D is a multiple of 3, then any pair XD with regularity, co-regularity maybe, equal to 1 is S equivalent to just the thing at the top. So somehow this is sort of backwards, right? This is like the most open point, not the most closed point, but it's still a representative. And then to actually prove the existence of this asymptotically good moduli space, in this case, what do? I'll just take 1 minute and tell you what we do. We, take this PDCY, and we decorate it with another number, which is not the regularity. Well, I'll put it at the bottom. Put it down here. M. And so this will be pairs where the index of X, so by index here, I mean the number such that NKX is Cartier, is, maybe I'll say N, less than or equal to M. So we stratify by this. So we just define the stack, and we prove, so part 2, for M sufficiently large and divisible, we show that these are S-complete theta reductive, and they stabilize. And by they, I mean these are S-complete, theta reductive, and they're common, excuse me, because they're finite type, because we have fixed this bounded index, they each admit a true good moduli space. Stabilize. And the key input is this top theorem. And so then we can just define the asymptotically good moduli space of this PDCY without the M to be this stabilization. And this, I guess, one, it proves that we have this well-behaved object, this sort of good moduli space. In many cases, it coincides with other moduli spaces we know. So if you have an additional structure, imagine if the degree is 6, then we're looking at pairs P2 1/2 a sextic. That's a Bailey-Borel moduli space of degree 2 K3s. We have the double cover. Our moduli space is equal to that moduli space. So our moduli space, if you do points on P1, is equal to the GIT of points on P1. So although this is sort of a weird asymptotically good moduli space definition, it recovers many different geometric constructions of different moduli spaces. And then we're able to actually use this to prove a couple of different things. For example, there was one of the consequences is proof of the semi-ampleness conjecture of Shukarov and Prokhorov in relative dimension 2 that says that if you have one of these vibrations of these sort of boundary polarized Calabi Yaus in relative dimension 2, there's actually an effective number for which the moduli divisor is semi-ample. I won't go into that at the moment, but ultimately, work of many others reduces that somehow to the case of P2, and then our work proves it for P2. So we expect this has several applications, and we expect that beyond the case of plane curves, we can prove something like this in more generality, and that's current work in progress. So I'll stop here. Thank you for listening.